All right, this is a Triton Rendezvous project where
There's a one gravity assist with Jupiter and it arrives at Neptune. All calculations for this trajectory did meet the requirements, but we thought we could make a better trajectory. So then we designed a third trajectory, which is a gravity assist with Mars. Ultimately, this trajectory did not work as it crashed into Mars. And the last trajectory that we created was a 2 gravity assist with Mars and Jupiter. This trajectory is going to be discussed in the future slides.
All right, so after designing 4 trajectories and comparing some of their characteristics, ultimately we decided on going with the 4th trajectory, which consists of the Mars and Jupiter flyby on the way to Neptune. So for some of the rationalization as to why we chose this trajectory, again, we compared all 4 of them and immediately 2 of those were eliminated. That being the direct home-in did not meet the system requirement of time of flight, and obviously the collision with Mars completely rules out that trajectory. Now between the Jupiter flyby and Mars and Jupiter flyby, we simply just took the one that had a greater margin of performance. So the Jupiter and Mars flyby, we were able to achieve a shorter time of flight as well as save on some C3 in terms of the total mission C3. And so that's kind of the basic rationalization as to why we chose this trajectory. Now for the mission timeline, from the very beginning, the launch date from Earth was on February 9th, 2031. We just launched from Kennedy Space Center, and the initial leg of the trajectory was 95 days to the Mars flyby. Between Mars and Jupiter, it was about 3,649 days. No, excuse me, it was 558 days between Mars and Jupiter. Then the final leg was 3,649 days to reach Neptune. And so that's kind of how the mission's supposed to look. We had the different C3 values at every leg of the trajectory, and that's the mission timeline.
All right, so delving deeper into the trajectory, we could then analyze some of the specifics behind it. One of the main assumptions, critical assumptions that we made, was that all of these planets are coplanar, which isn't real in reality, but for this project, it simplifies it a lot. If you're looking at the first pork chop plot shown on the board here, you can see that we wanted to leave with a low C3, just because so it could fit within our mass budget. And so on the left pork chop plot, you can see the area that we chose C3 from, and on the right pork chop plot, you can see what we arrive at Mars with. So we leave Earth with around 80 C3, and we arrive with about 300 C3. The time of flight for this transfer is 95 days. The next pork chop plot you can see on the board is the pork chop plot from Mars to Jupiter. We arrive with the same same C3 that we departed Mars from, which is about 300, and then we arrive at Jupiter with about 80 kilometers per second in C3. This transfer takes around 575 days. This last pork chop plot that's on the board, you can see that we arrive at Neptune with the same C3 that we departed Jupiter with, which is around 80 C3, and we arrive at Neptune with around 140 C3. This transfer takes around 3,650 days.
All right, so in terms of our mission design process, once we have looked at the pork chop plots and kind of had a general idea of what our time of flights and C3 parameters are going to look like, we proceeded to optimize the trajectory using the code written by Dr. Marco Maggia, the interplanetary transfer MATLAB code. So the parameters didn't change that much, but we were able to narrow down a more precise trajectory. So the C3 values just changed within a margin of about 10, and the time of transfers changed with about a difference in a day or so for the last leg of the transfer. Again, it wasn't a very different magnitude and margin, but we were able to maximize and squeeze out every possible bit of C3 for the transfers, and as well as reduce the time of flight total.
So right here we have our departure launch window. We decided to launch from Kennedy Space Center. When you launch from the Space Center, you have a minimum azimuth angle of 35 degrees and a maximum of 120 degrees, so you prevent collisions with like other states or possible things. The azimuth angle that we chose to launch from is about 45 degrees. All right, now delving deeper into the flybys of the trajectory. The first one we do is at Mars. we have the C3 upon arrival and the velocity vector for that C3, and the C3 upon departure being the same but with a different velocity vector. With these two velocity vectors, we can calculate the orbital parameters of the flyby. Some important ones that we considered was the altitude that we passed by with, just in case we crashed into the planet, it wouldn't work. Also, the eccentricity of the flyby is very important, as well as the turning radius and the aiming radius. The next flyby that we did was with Jupiter. The arrival C3 was around 78.48. And again, we have a different velocity vector than the departure velocity vector. And from these velocity vectors, we can calculate the orbital parameters shown on the board. Like I said, the altitude is a very important consideration because if it's negative, then we do crash into the planet. The eccentricity, the turn angle, the turning radius, as well as the delta, very important parameters.
So once we had calculated and determined all of our flyby geometries and what they would kind of look like, we could proceed to figure out how we wanted our parking orbit to look like after capture around Neptune. So the process that we used to come up with these determinations was to see the relation between radius of periapsis around Neptune as well as the orbital energy or orbital velocity that would result from different radius of periapsis. So based on this, we selected a radius of periapsis of 197,000 kilometers. The reason for this is we wanted to reduce the necessary C3 that we would have to burn in retrograde in order to capture this orbit. And so the C3 retrograde burn that we needed was about 33.4 kilometers squared per second squared. And again, we use this to account for the mass budget. By reducing the magnitude of the C3 needed for burn, we could avoid having to carry more mass at departure. So for the mass budget, kind of tying in with our design of all the flybys and the capture orbits, we started with the total amount of C3 that we needed for the entire mission. So we added up, again, the C3 at each impulsive burn, which we came up with a total C3 required of about 107.11 kilometers squared per second squared. Based on that, we used this SLS to C3 capability chart, which we found on the NASA SLS handbook. We were able to determine the maximum mass that we could carry with that necessary C3 at departure. Now here we have a visualization of the mission. Some simplifications here is that we didn't account for any staging of the rocket. So obviously the boosters will be shown throughout the mission. And then we did speed up the mission at certain key times just to highlight the flybys and skip through the long third leg of the trajectory. So right here we see us in the flyby past Jupiter. After this, on the last leg, again the longest time of flight, we can see the rocket is on course for the last and final impulsive burn for capture. Another thing to note is the coplanar assumption is also present in this visualization, so any kind of plane change that we would have to make wouldn't be present, as well as accounting for the Triton orbit around Neptune obviously isn't being visualized as we weren't able to achieve that system requirement in this design. And finally here, after capture, we see we established an orbit around Neptune. Again, it's just a generalization, so the orbital period is a little bit simplified.
So in summary, we used different programs such as MATLAB, Blender, Microsoft Excel, and Microsoft PowerPoint in order to make this project possible. We did compare multiple launch dates, and in conclusion, we did launch from Kennedy Space Center with 2 gravity assists and arrival at Neptune on November 21st, 2042. And here we have a compliance matrix which shows like all the categories which are compliant, and as recently discussed, the lunar transfer was non-compliant in this project.
And this is just the appendix for the different tools we used to design this mission. Thank you.
Thank you for watching.